Hello, welcome to our Capstone Project video presentation. My name is Chris Zarba, and our team members are Sultan Alzabi, Peter Zico, Mike Selesnik, and Matt Heim. For our project, our goal was to implement a brain-computer interface system to allow people with physical disabilities to play video games. We hope to accomplish this by using visual evoked potentials. A visual evoked potential is a brainwave pattern caused by a visual stimulus, such as an alternating checkerboard pattern on a computer screen. We specifically focused on steady-state visual evoked potentials. SSVEP is produced when a user observes a stimulus such as a flashing light at some frequency or repeated pattern. The visual cortex will create brainwaves at the same frequency or pattern. By flashing our visual cues at different frequencies, we are able to measure which one the person is looking at, and therefore which game input they want. So why choose this method? There are other existing methods that achieve a similar goal, like a breath-controlled gaming device or an eye-tracking device. However, Northeastern professor Dennis Erdogmas, who we consulted with, published a study that found that VEPs are more accurate than eye tracking. Additionally, some people with physical disabilities can struggle with breath-controlled devices. This block diagram shows an overview of how our system works. The user wears a headset that reads EEG signals and sends them to our software. The signals are processed and filtered, and then a machine learning algorithm finds their correlations to our possible target values. Then our input classification model chooses the most appropriate target for the data and sends an input to the game state. The game state is displayed on the monitor, which is surrounded by the visual cues which the user looks at to select their next action. During our project, some difficulties we encountered included the EEG data being inaccurate, being unable to verify the integrity of our signals, and our original UI program library being unable to display consistent frame rates for our VEPs.
For our hardware, we decided to use the Emotive Epoch Plus headset. Sadly, we later discovered that this device isn't the best for EEG signal extraction. The headset consisted of 14 channels resting on various parts of the brain and acquired 128 data samples per second. In our research, we found that similar products in BCI also utilized Emotive for their source of EEG signals, plus the product was commercially available for around $600, so we felt comfortable buying it, knowing that we wouldn't need to purchase any more significant materials. One of the initial draws of Emotive was a well-documented Cortex API that would allow us to easily acquire data and format as we desired. It should also be noted, however, that in our discussions with Professor Erdogmas, he was not as optimistic about the Emotive headset as we had been.
Our initial approach was to use the Python library PyArcade to create a UI that draws the stimulus and game at the same time. In order to run the Game Boy ROMs, we implemented the PyBoy library and worked with the devs to take image information from the emulator and draw it into our PyArcade window. To handle the stimulus, we drew checkerboard icons around the game that the user could look at to pick a command. The checkerboards were chosen on proof of them working in past studies and would flicker by having their colors inverted on each flip. We realized that we would need to create two windows, a data collection window to get training data for our models, and a live mode window where we can test the models we create and play the game. The data collection window mimicked the live mode without the gameplay. The live mode window would subscribe to the Emotive EEG data signal and constantly collect the latest EEG data on every frame of the game. Every X amount of seconds, we would send this data to a command handler that would filter and make a prediction on the filtered data. The prediction would be mapped to a command, for example up, down, or A, and would send that command to the PyBoy emulator to progress the game. Unfortunately, there were unforeseen issues with this library. The timing between frames was inconsistent. Since PyArcade couldn't deliver consistent times between each frame, we were unable to collect data in a consistent manner. Without good, clean data, we can't capture the VEPs in our brain caused by the flickering icons, and this bad data means that no classification model would be able to make accurate predictions. This results in the game being nearly unplayable.
To handle the inconsistencies of PyArcade, we had to switch to a different library. We were recommended CyclePy by Professor Erdogmas. Our main concern here was the time it would take to recreate the whole project in CyclePy. However, CyclePy was designed to be very easy to use and specifically to run a wide range of experiments in the behavioral sciences. Therefore, we utilized its builder GUI and coder IDE to quickly put back our project together. Now, the project was more complete with the frame inconsistencies handled by CyclePy. We made some major changes to our project as we transitioned to using CyclePy in order to step towards our goal of a proof of concept. First, we changed the checkerboards to simply be flickering white icons. Second, the look of the UI was a little bit different. We also went down from 8 commands to 4 commands only. However, when tested with simulated EEG data, the system can also work with 8 commands. The Builder GUI made it very easy to build the new project by utilizing routines and loops. Then, we compiled the Builder project into a Python script. From there, we simply added our old code and modified some smaller features, and then the project was ready for testing. When we transitioned to using PsychoPy, we decided to follow one specific research paper. This research paper suggested the use of an offline mode and an online mode, similar to our data collection and live mode. This video shows one of the team members recording EEG data. The program randomly selects an icon and highlights it in red to indicate that the user must stare at that icon. After recording EEG data for that icon, the program selects another icon randomly. The program will go through all the icons every cycle, and will run this experiment for a set number of trials.
With the signals from the headset acquired, we needed to pre-process this data before passing it into our classification models. First, we considered several methods of signal filtration. Per our research, the signals our brains send during visual stimuli are in the neighborhood of 7 to 32 Hz, so we knew those were the frequencies we should focus on. Our methods included a Butterworth bandpass filter and a finite impulse response filter to eliminate higher frequencies. We also used a method called principal component analysis to reconstruct the signal from its strongest channels, as well as a fast Fourier transform to view our signal in the frequency domain and gauge the performance of our filters. As we can see, applying PCA filtering to our original O1 signal, which is in blue, produces a more stable output, seen here in orange.
One of the approaches we took to identifying commands was to use neural networks. Although we have access to 14 sensors for data, we determined that only the 2 occipital and 2 parietal sensors would be needed as they measure visual data most closely. Using less sensors also meant that there would be less training parameters, which would reduce training time, and also potentially reduce noise from other sensors if they're not measuring the VEPs we're looking for. We used TensorFlow in order to implement both of the neural network architectures we tested to classify this data. The first neural network we tried is a long short-term memory network that has recurrent gates. This allows the network to recognize and classify sequences of data. This means that it can input the entire length of 1 to 3 seconds of EEG data that we recorded when the user was looking at one of the flickering icons. The output would be between 0 and 7, trying to guess which of the flickering icons the user was staring at. Our other attempted method was a standard dense feed-forward network, in which we use power band data so that we can work with an input array of integers instead of data sequences, which are compatible with this network architecture. For this, we focused on a split of low and high power band data in both the alpha and beta wave ranges. This is where we expect to see the VEPs, so this is the data we fed the network in order to guess which icon we were looking at. Both networks show nearly random guessing results, most likely due to bad data issues instead of the network architecture we were testing.
The second classification method we used is CCA, or cross-correlation analysis. CCA is useful in decomposing and analyzing a multi-channel signal. CCA is part of a family of algorithms that finds linear relationships between multivariate datasets. First, we filter the data using a bandpass filter to remove low and high frequency noise. We generate sine and cosine waves at each target frequency along with the second harmonic. Once we have the reference signals for each target frequency, CCA finds 2 canonical correlations between the measured stimulus and each reference. So for 4 targets, there are 8 canonical correlations. These canonical correlations are used as features for KNN, or K-nearest neighbors. KNN is trained and tested on offline data with the correct target as a label. CCA can also be used to classify by choosing the target with the maximum correlation score. Using actual EEG data with 4 targets, our KNN accuracy reached at most 50% or 25% above random chance. CCA had a high variability of accuracy, ranging from around 5% to 80%. It seemed to be much more accurate on the lowest target frequency rather than the higher ones. We were unable to make accurate predictions with the EEG because there was not a high power at the desired target frequencies as indicated by these power spectrum plots. Many times the power spectrum was the same across offline data for different targets. To go around this problem, we decided to create VEP signals for each target frequency. These signals are sine waves with additive and multiplicative Gaussian noise along with some low frequency noise. Here are some examples of generated signals. The power spectrum of the time data shows a spike in each target frequency and its second harmonic. We did not find spikes in our actual EEG data as other research typically has. The table shows KNN's accuracy with different levels of noise and different stimuli length. For verification, we used the simulated data to play the game with the keyboard. While this is not truly playing with the EEG as we initially planned, it demonstrates the steps of our data pipeline. Once the data is updated, it is filtered using a bandpass filter allowing frequencies between 0.16 and 50 Hz. Our controls and the order of targets are the A button, B button, up, left, right, down, start, and select. The relatively prime frequencies we used were 43, 37, 29, 21, 17, 11, 8, and 5 Hz. Numbers 1 through 8 represented those buttons, and the arrow keys were also mapped to the same targets as numbers 3, 4, 5, and 6. Each key represents a different target frequency, and pressing a key regenerates a 3-second duration of the VEP signal with random noise as described before. Every frame, the 3-second VEP signal is fed into CCA, which makes a prediction and sends the appropriate command to the PyBoy controller. To include non-action, we only selected a target if there was a CCA score higher than a threshold of 0.3. I show walking around the map and battling in this video.
We would love to be able to continue working on this project with a better EEG headset. If we had better hardware, we are extremely confident that we could achieve the intended results. We believe our machine learning and our data filtration code was very well executed and would work with sufficiently good data. If we were to continue this project, we would first buy better hardware, then verify the hardware worked and change any necessary code to work with that new hardware. After that, we are confident that the rest of our project would completely work and we would be able to deliver the finished product as originally intended. Over the course of this project, we as a group learned a lot about machine learning, a subject which we tackled despite none of us having a background in it. We learned about VEPs, data filtration, dimensionality reduction of data, and a lot about machine learning classification models and the different ways to use them. We also learned about being careful consumers and making sure to only buy products that we are sure will work. We would like to thank Professor Kamani for helping us with this project and Professor Odogmas for consulting with us on our many machine learning and VEP questions. Thank you for watching our video presentation.